Okay. So we are going to focus on atomic structure in terms of how many protons, how many electrons, and how many neutrons there are. In physics, if you continue in physics with physics, you might talk about quarks and neutrinos and what's happening inside a nucleus. But what's important for us is how many protons, how many electrons there are. Changing the number of protons in a nuclear reaction can get you a new element. Changing the number of neutrons makes something called an isotope, which we use for radiation therapy, stuff like that. We'll talk about that tomorrow. And then changing the number of electrons is what chemistry is. That's what makes a reaction, is either sharing or transferring electrons. So we're going to focus on these three particles. So the atomic mass on your periodic table is reported as an average. For now, we're going to use sometimes AMU, sometimes this little fancy mu symbol, or sometimes simply just a U. And then eventually when we get to unit 3, we'll look at a different unit for the atomic mass. And it's an average. So that's why it's not a whole number. So today, when we count the number of neutrons, protons, electrons, then we're going to round it because you can't have 0.5 of a neutron, for example. So we'll talk about what an isotope is tomorrow. We'll look at how to calculate the abundance of the isotopes as well. So you can Google, if you Google the atomic mass of hydrogen, it would give a different number of decimal places every time. Ours actually stops at 8, so they round that last one. They have 3 decimal places. You can find even more. So it just depends how precise your equipment is. So sometimes they use these symbols for atomic number and for atomic mass. I don't know, chemists are lazy, so it's easier to write down Z for atomic number and A for atomic mass. And they can both be found on your periodic table. So if you look at your periodic table, it actually has this little carbon thing here. If you forget where to find the information, it tells you. So the atomic number is in the top left, and the periodic table that we use is ordered by atomic number. Then on the right-hand side is atomic mass. That's what we need today. The oxidation states or the charges, we're going to use that later on when we get into naming. Okay, so for now, you just need the top left-hand number, which is the atomic number, and the top right-hand number, which is the atomic mass. There are many different forms of a periodic table. Your textbook has one at the back of the book. It is, I can't print color, but it has colors based on state, so that can be useful. It just depends. But this one is the one that you're always going to get, because if you look at the back, it has the other reference information that we need over the course of grade 11 and into grade 12. So for proton, we usually use the symbol P+, capital or lowercase, it doesn't matter. We say that protons have a relative charge of +1. So technically, if we look at charge like how many volts or coulombs something has, that is not what its charge would be. But again, for chemistry, because we're looking at how electrons are shared or transferred, that's good enough. How many protons are there in relation to how many electrons are there? And that makes ionic charge, that kind of thing. So that's why it says relative charge. We're going to use that to say if you have 1 proton, it's +1, 2 protons is +2, etc. It has a mass of approximately 1. So that is similar to a neutron. And then electrons are tiny, 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 and essentially we call them weightless, or their mass is negligible. So they are located in the nucleus of the atom. So when we review Bohr-Rutherford diagrams, that's where you should put the number of protons inside the nucleus. And then, This is probably underlined if you want to highlight it as well. The number of protons is determined by the atomic number. And the number of protons where the atomic number is unique. You can have the same number of neutrons, which is not common, and you can have the same number of electrons, which is the whole point of chemical bonding, really, where you have ions and that kind of thing. But the number of protons is unique. It is the atomic number, which again, if you forget where that is, your periodic table tells you. And you're always going to get this version. I'm not going to white stuff out, okay? It looks like this, what you have, okay? So the periodic table, like I said, we use is ordered by atomic number. So the number of protons then is the atomic number, which determines the identity of an element. So if you change the number of protons, which you can only do by fusing atoms together or breaking them apart, or fission, which is nuclear changes, then you can make a new element. And that's why nuclear reactions or nuclear changes are accompanied by so much energy, because you're actually creating new elements by fusing nuclei together or breaking them apart, which again, we cannot do back here for the health of your future children, and no blowing up Brantford, okay? No nuclear changes. So electrons, we use an E, usually a lowercase e, but that doesn't matter. So again, we're going to say it has a relative charge of plus or minus 1, so protons +1, electrons are -1. So if you have 3 electrons, that's a charge of -3. So it is tiny, tiny, tiny. So we say it contributes nothing to the mass of an atom. The word negligible means that you can ignore it, basically. Sometimes we use that word in math as well. For example, when you factor and you find the 2x values for a quadratic equation, if it's time and one of them's negative, you can't go backwards in time, that kind of thing. So we ignore it. So tiny. They are located around the nucleus, so that's where we're going to draw them. And they determine the chemical behavior of an element. So when we talk about trends in the periodic table, why is something more reactive than something else? It is going to be based on the number of electrons, specifically valence electrons. So the neutron, we say, has a charge that's supposed to be a 0. This is a wacky font. Okay, so neutrons have 0 charge. They are neutral. However, the reason they are important is that they have a mass. So we say they have the same mass as a proton, which makes an element heavier, and it helps to stabilize the nucleus. When they first described an atom, it was experimentally easy to prove the existence of electrons and protons, because a positive and negative charge can be attracted to the opposite charge. However, neutrons obviously don't do that, but the element wouldn't have been the nuclei. They couldn't explain the stability of a nucleus without the presence of something else. And if electrons were tiny, then they needed something else in the mass of an atom. So protons and neutrons, they go inside the nucleus. So again, that's where you're going to put them when you do a Bohr-Rutherford diagram. So they will form what we call an isotope. And we'll talk about isotopes tomorrow and how you can figure out what kind of isotopes exist. So there are some elements that have stable isotopes. There are some elements that have isotopes that decay and release radioactivity, which we use as humans. We use that all the time for different purposes, which we'll talk about tomorrow. Okay, so the atomic number tells you the number of protons in the nucleus. You never, you're not going to memorize the first 20, nothing. You never need to memorize the periodic table. You're always going to get this. So you can look at the atomic number and know the number of protons. Today, for now, when you do the worksheet, etc., then the number of neutrons is going to, the number of electrons will be the same, because we're going to deal just with neutral. Okay, so like I said, the protons is unique. Oxygen has 8, nitrogen has 7, helium has 2, etc. Just look at the atomic number. The atomic mass number is the total number of protons and neutrons in an atom. So today, if you're filling in the chart and you're looking for the number of neutrons, you do need to round the atomic mass, okay? So you're not going to do, for hydrogen, for example, 1.008, you would just use 1, okay? So the atomic mass number, again, is an average. You have to round it. Most of them are really straightforward. Sometimes people will look at chlorine because it's listed as 35.45. So then that rounds to 35.5. Should it be 36? We usually just use 35. So try to keep it as simple as possible, okay? Don't make it harder for yourself. So the number of electrons is the number of protons. That's what we're going to do today, neutral atoms. So if you want to highlight that, there are lots of dots there, or stars. And then the number of neutrons, you round the atomic mass number and subtract the number of protons. If you're into symbols, A minus Z. If you're not into symbols, that's fine too. And another thing you can use to represent atoms is standard atomic notation. So what we do is the symbol, and then on the left-hand side goes the mass number, and the atomic number. So the way that we do that, you put the bigger number at the top and the smaller number at the bottom, maybe as a way to remember it, but it's always, and do the rounded mass. If you put like for hydrogen, if you put 1.008, I wouldn't take marks off, but usually when you see standard atomic notation, they just use the rounded mass. I don't think the example printed. So it's this is helium. Helium is number 2. Its mass is 4.003. So you just round it to 4. Okay, after that is a worksheet you should do, okay, for tomorrow. But let's do this first. Let's do Bohr-Rutherford diagrams, and then I'll stop talking and you guys can work. There are extra questions in the textbook as well, if you want even more practice. Okay, so this is after the chart. Everybody see it? Okay. So I'm going to show you what I want you to, what I'll accept for Bohr-Rutherford diagrams. I know that some grade 9 teachers are very particular. Really what I want you to do is show a nucleus, the number of protons and neutrons inside the nucleus, and then outside the nucleus go the electrons. We're going to use these Bohr-Rutherford diagrams to help us visualize the number of valence electrons, and then we are going to use it for ionic charge, and that's really the end of the usefulness of these. The first unit in grade 12 is basically showing how Bohr-Rutherford diagrams are incorrect, or not a sufficient model for the atom. So we're going to use the maximum amount of usefulness they have this unit and then really never again, okay? So hopefully your grade 9 or 10 teacher did not make you go past 20, because even when we do calcium and potassium, we're sort of fudging the rules a bit that we teach you, but it works, okay? So let's do, what's a good one? Let's do nitrogen. So nitrogen is element number 7. So that means there are 7 protons. We'll just stick with atoms today. 7 neutrons, or 7 electrons, sorry. And then the atomic mass is 14.01. So I'm going to round it to 14. Minus 7 is 7. So make sure you make a nucleus. Okay? Inside the nucleus should be protons and neutrons. Doesn't really matter which one you write first and which one you write second. Most people do the protons first because that's the easiest to figure out, but it doesn't matter. Okay, and this is where I know some teachers will make you do stuff like this, and it has to be like perfectly far away and all this kind of stuff. No. And really the reason for it is, like I said, there is very limited usefulness to these. So we're going to exploit the usefulness as easy as possible. So in the first shell, go 2 electrons. In the second shell is a maximum of 8. So we already have 2, so that's going to be 5. And that's all you have to do. If you want to do the perfect dot one, where it's like, I know some teachers even make you, don't they make you like line them up? Like they all have to be right in the same spot. That's fine, you can do this. You don't have to. It's important you know how many protons there are and how many neutrons there are. They have to go inside the nucleus. Don't do things like this. Okay, that's not a nucleus. Okay, that's not what we're going to do. And we need to know a couple other things. We need to know how many valence electrons something has, or the outer electrons. That this version tells us that. We also need to know how many shells there are, which is 2. You could also tell that by the periodic table. We will talk about this again tomorrow, but you can kind of check. So first row has 1 shell, second row has another shell. So then if you go 1, 2, 3, 4, 5, 6, 7, 8, that's where he gets the 8 from. And then technically, then the next one, he says 1, 2, 3, 4, 5, 6, 7, 8. And that's why we make a 4th one for calcium and potassium. But you'll see next year that that's where things sort of start to fall apart, okay? But that's okay, it'll work for us. So you can look at how many valence electrons there are, which is related to the columns. How many shells there are is related to the periods, okay? But for today, so on the next page, I even tried to truncate the periodic table. Only the first 20 are on here. So it goes in order: hydrogen, helium, lithium, beryllium. I've just cut out the gaps, okay? So you can decide what kind of Bohr-Rutherford diagram you want to draw. If you are not sure, first of all, you can ask me, but second of all, use a pencil, okay? Once you do the Bohr-Rutherford diagram, then you can do the Lewis dot diagram. Now, a couple things about this. Maybe you remember how to find the valence electrons, that's fine. Or do the Bohr-Rutherford diagrams first, and then to do the Lewis dot diagram is easy peasy, okay? What sometimes students are like, Mrs. Todd, aren't these called Lewis structures? What we're going to do next, after trends in the periodic table, is we're going to look at a Lewis structure for a compound, like NaCl, CH4. So I prefer that these are Lewis dot diagrams because they are just elements by themselves. When you put them with other elements, that makes a structure, okay? If your grade 9 or 10 teacher called these Lewis structures, they're not wrong. Again, we just to try to differentiate between the two, okay? So Lewis dot diagrams, whether it's a structure or a diagram, it's going to be concerned with valence electrons only. So that's why if you forget or you're like, oh, this was a long time ago, then draw the Bohr-Rutherford diagrams first, because that will help you do this, okay? So what I wrote here, it says fill in the electrons one at a time, and then I said top right side. It's kind of like never eat shredded wheat, right? So let's say we do nitrogen. Back here, nitrogen has 5. Oh, so if you forget what valence is, those are the outer ones, right? Or the last shell, okay? So it has 5. So you don't do this, right? No, okay? What we're trying to show is how they are actually arranged. So electrons do not like each other because they're both negative. So what happens is the best we can get with electrons is a pair, okay? So what you do, never eat shredded wheat, and then go back and, pair them up. So they will be as far apart as possible. So something like carbon, which has 4, does not have any pairs, okay? So you have to go never eat shredded wheat and then start to pair them up. You draw this, that's not right, okay? Because what we're going to do next is draw the structure. So this is going to help us figure out how many bonds carbon needs. That's what we're going to do next in grade 11. And then in grade 12, we're going to look at, based on how many bonds there are, based on how many pairs are left over, then we're going to say, okay, what's the 3D shape? So we're going to think about 3D, okay? So it's not that we're being persnickety about this. This is the best way to represent really what actually happens, okay? The best we can do with electrons is pairs. And when you talk about bonds, 1, 2 electrons makes a bond, right? So it all kind of goes together, okay? So right now you can do the safety crossword. If you have Wi-Fi or you have copious amounts of data or whatever, you can do the SDS sheet. Technically, the SDS sheet is for Thursday. None of that information is on the safety quiz, nothing specific. I'm not going to say to you, what's the symbol for hydrochloric acid? No, that's just information you guys need so that you know in a very basic sense when we go to do a lab, oh yeah, hydrochloric acid. Again, I will totally remind you, I am not going to set you up to do something crazy back there, okay? But just so all those chemicals we're going to use over the quad, so you can do that. Or in addition to, you can do this sheet, okay? Especially standard atomic notation. I don't know why students often forget which way it goes, so make sure you do that last column. The answers to this are on D2L, so you can check when you're done. And then I'd like you to have this finished as well, okay? The rest of it, if you have copious amounts of time tonight and you want to do it, that's fine. But if you are especially if you're a fast test writer, you will definitely have time tomorrow. So if you want to save the rest until tomorrow, that's perfectly reasonable, okay? Or if you're like, you know what, I want to quickly review the lab equipment or whatever, okay? So I get that too. Just as an aside, I don't mind, especially obviously